In the first section, we discussed vertical ventilation, why it's used, and some of the challenges that come with it. In the second video, we looked at how to size up and think about what a fire is doing. In this video, we're going to look at the really cool part of this, which is fire flow paths. We've mentioned them before, but what is a fire flow path? Put simply, it is the route that air and oxygen take to come in and feed a fire, and the route that the heat, smoke, and hot gas byproducts go as the fire is burning. As fire burns, hot gases fill the space around it, and this creates a high pressure environment. What does high pressure in the atmosphere want to do? It wants to equalize by finding areas of lower pressure to move towards. In the simplest terms, the compartment fire environment will always try to do two things. It will try to equalize pressure by moving from an area of high pressure to lower pressure, and it will always try to move towards or draw in oxygen to feed itself. In the last video, we started off by looking at the fire triangle of heat, oxygen, and fuel. Now let's review the methods of heat transfer: conduction, convection, and radiation. Conduction occurs by direct contact with an object. Radiation occurs by absorbing the heat being emitted from a burning object. Our PPE is designed to protect us from radiant heat. Convection is how gas and fluids heat, and this tells us a lot about how these flow paths work. Let's watch this short video on convection, and then we'll start talking about how this applies to our burning buildings.
Convection. So, we've looked at conduction and we found that both liquids and gases are rubbish at it. But heat can transfer through them fairly easily, and the way it does this is by convection. Convection occurs only in fluids. Now by fluid, we just mean a liquid or a gas, something that can flow. And the way it happens is always the same. So, let's look at the gas particles in this room. They all have roughly the same energy, which we can see because they're all moving about the same speed. So let's put a fire in the room. Okay, now the particles by the fire start to gain energy from it, and they start to move faster. And because they're moving faster, they spread out. So that bit of fluid becomes less dense. And because it's less dense, it rises. Now, when those particles rise, they can't leave nothing behind. So the cool air or fluid moves in to replace them. But now this cooler fluid is by the fire. So these particles start to gain energy. And this bit of fluid then becomes less dense than the fluid above it. And it rises, pushing the other particles back round. These are now back by the fire. So guess what? They're going to gain energy. They're going to get even hotter. They're going to become even less dense. They're then going to rise. This is going to happen over and over again, forming a convection current. And that is how heat transfers through fluids, liquids and gases. So, what are the key points here? Well, the key points are that in convection, fluid near the heat source gains energy, becomes less dense and rises, being replaced by cooler fluid, which then in turn gains energy, becomes less dense and rises, forming a convection current, which then heats the fluid completely.
So that sets the stage for us to start looking at these flow paths. We're going to look at two types of flows: bidirectional flow and unidirectional flow. A bidirectional flow has a fire burning in a room with one opening. Cool air comes in along the bottom of the opening and hot gas escapes out the top. This is a very inefficient flow path for a fire. As the fire displaces more and more byproducts of combustion, more smoke and more heat, if that opening is too small, it becomes a bottleneck, effectively vent limiting the fire, even though there's ventilation present. A larger opening, however, in proportion to the size of the fire, will make for a free burning fire. In this video, we see the telltale bidirectional flow: cool air running along the floor to the base of the fire and smoke rolling out the top. This fire inside a large open container on one side with pallets burning is essentially fuel limited. It has plenty of air available for the size of the fire, the amount of fuel there, and the size of the opening. In an actual furnished room with a single window or door, this may not be the case. This is the classic flow path we see on a vent-limited house fire when we open the front door and cool air draws in towards the fire and hot smoke rolls along the ceiling. Temperatures along the floor will be cool, while temperatures along the ceiling will be much hotter. Let's look at another type of bidirectional flow. In this example, we have two openings of equal size and height. Again, this is an inefficient flow path. Fire is drawing cool air from below on both openings and trying to vent smoke along the top of both. This fire still can't freely breathe. Now let's talk about a unidirectional flow. This is a very efficient flow path for fire growth. If we have two openings, one higher than the other, this allows for the lower opening to be the fresh air feed to the fire, and the upper opening being the release for smoke, hot gas, and where the pressure wants to go to equalize. The higher opening is where we can expect the highest temperatures and the fire to migrate towards. The reason vertical ventilation works so well is it draws heat out the top, and that is this model. What this also does, however, is remove all ventilation restrictions on fire growth. If the fire is not contained, it now has the optimum conditions for development. This is also the flow path that occurs in a below-grade or basement fire. To access this fire, we would enter through the front door, which is higher than the fire. That's fine if there isn't an opening below us. What happens, however, if a casement window fails, or if uncoordinated ventilation on the outside occurs, or if we miss something during our size up? All of a sudden, we are in the exhaust pipe that is moving faster than we can move, pushing heat that we can't see through our PPE. At one time, the teaching was to protect the stairs. The problem with that is no amount of water put on this moving air current is going to cool it. The only thing that will cool this flow path down is water applied to the seat of the fire. You'd be better off closing that hollow core door to the basement and closing that flow path off than you would be putting water on the ceiling. And while this is the principle of how vertical ventilation works, it's also how it cannot work if it is not coordinated properly. Ventilation doesn't cool a fire. Introducing oxygen always feeds the fire. It will always drive heat release rates and temperature growth. The only thing that cools fire is applying water to the seat of what is burning. Let's look at it in these two attic fire videos from UL. In this video, we can see vent-limited conditions and pressurized smoke in the attic space struggling to leave through the eaves and gable vents. Once the firefighters open up the ceiling inside, the fire gets some opportunity to breathe, but is still vent-limited. Once they apply water to the fire, you can see the steam expansion work and displace more of the smoke through the gable vents. In this video, the fire is in a free burning state. It has a unidirectional flow path with cold air being entrained through the open door and the open ceiling, and an opportunity for the hot gas to escape through the ventilation holes cut in the roof. Firefighters come in and apply water and attempt to extinguish it. They can knock down the flames that they can see, but the fire has such an opportunity to develop through the attic space that it can't be extinguished. Now we've added a few more pieces to our size-up considerations. In addition to whether the fire is vent limited or fuel limited, or if it's involved just the contents or the structure, now start to think about where the fire is located and what type of flow path it has feeding it. We're going to put this all together in the next section.